All right. Hey, everyone. So we're going to get to know each other a little bit today. So if you would humor me, poor first-time major conference speaker, please come up to the front if you're all the way to the back so that you can kind of feel my energy and then I can feel yours. Only if you feel like it, but it'll be really nice that way. It'll be really intimate. And then I get to ask you some questions, and then it'll be a fun session. Awesome. Thank you so much. I love this crew over here with the red jackets. Super awesome. All right. OK, so first question. How many of you have done a hardware project before? Yes? OK, some people, great. I hope you learned something new today. And how many people have tried to do a hardware project or didn't know where to begin or thought that it was too hard? OK, perfect. I'm glad to know I'm not alone. I was there, too. Doing anything with circuits and hardware always seemed like something I could not do. When I was a kid, I would take toys apart, especially the ones with the batteries, and try to figure out how they worked. But I would never be able to put them back together, and my mom would be very upset. And apparently, moms don't take photos of broken toys, so I have a stock photo to show you instead. Fast forward, I went to a university that separated CS, computer science, from CSE, computer science and engineering. The difference was the requirement of several hardware and electronics-focused classes, and the gloating of my CSE friends that what they were doing was real engineering. I was very interested, but then I remembered all of my broken toys and all of the failures that I've had as a kid trying to put them back together, and I decided to take CS instead. And of course, I loved programming. So all of my coding life, the answer to this classic question, how many software engineers does it take to change a light bulb, is, everybody, none. It's a hardware problem. I let this distinction between software and hardware lead me to believe that hardware was just too hard, and it was something that I would never learn. Fast forward again, a few years after college, and this distinction was no longer as crisp. And I began again to be curious about hardware problems. I had a bunch of ideas, but I had no skills to do any of them. And so I decided that I would at least give it a try. This was my first failed attempt at learning anything about hardware and circuits. The idea was, does anyone here play ping pong, table tennis? OK, great. I do not. But I always get asked to keep track of scores. And so I thought, well, what if I just create a couple of buttons, one for each team, and they could keep track of their scores themselves? And then it would update a live scoreboard. Despite what that red button says, it was not easy. I had no one to guide me, and there were no good tutorials around that I could find. And plus, the ones that I did find had too many abbreviations. GND, VIN, ESP8266, SCI. I mean, WTF. And so, after this entire debacle, I decided that hardware was definitely not my thing. I am a software person. That's it. I set my dreams aside. And then I found Twilio SignalConf 2017's HackPack v3. It is their badge for that year. It's got this thing called a particle electron on it, and it's got this matrix of lights. And you can text stuff to it, and it does things. I was really fascinated that somebody wrote some code and then put it into this thing, and I was literally holding it in my hands. And I thought, I already know how to use the Twilio API. Maybe if I can just figure out how they made this, despite all of my failures and all of my broken toys, maybe I can hold my code too. And so, right around that time, my coworker asked me a genius question. He asked, what if you could make a hat that would light up depending on the state of an Uber ride? I couldn't believe he was asking me this question. It was like the universe wanted me to learn more about hardware. Hashtag GitHub Universe. And so I told him, yes, we can, absolutely. Even though I had no idea what I was talking about. So I ordered a particle electron, because it maybe worked with APIs, I don't know, really. And then I flowered around some more, and then I made this. It's a shark hat with a 3D printed unicorn horn on it, and it lights up depending on the state of your Uber ride. I think I met my coworker's requirements. Thank you. I took it off because I want you to take me seriously. OK. This project became my gateway project, really. Through this project, I learned a ton of things, and it gave me the courage to push through all of my fears and all of my many broken toys. And I've been making one thing a month since January, and I would like to share what I have learned with you. Hello, I am Charlyn Gonda. I am a coder by day and a maker by night, and I hope that you will join me in being one as well. Today, I want to achieve two things. One, I want to teach you how you can make your first IoT wearable. And the hope is that you will take the knowledge, the pieces of knowledge that you gain from this one example, and apply it to your other projects, whatever your heart desires. And number two, I want to remove all of your fear and hesitation in starting a hardware project. I want to, one, expand your problem-solving tool set, and two, really, I want you to experience how fun it is to pull your code out of the screen and into the physical world. So the good thing is, you probably already live and breathe the internet. So you're basically halfway there. I'm here to talk about and teach you the of things part. Let's get started. These slides are going to live here, so don't worry about missing anything, and I will show this link again at the end of the talk. OK, first, a couple of quick definitions. A microcontroller is basically just a small, tiny computer. It's got CPU, it's got RAM, it runs programs, and maybe it connects wirelessly. So it's not a scary thing at all. It's our new, happy, little dancing friend. And for the duration of this talk, I might, instead of saying microcontroller, say board, because microcontroller is kind of a mouthful. And at some point, I'm going to talk about flashing code. That just means the act of putting some code into your board. OK, let me pause here for a second. The general idea is that you take your board, you flash some code into it, and then you put it into a thing that you want to control. And depending on whatever development board you choose, that thing could either be directly connected to the internet via some cellular connection, or it connects to the internet via Wi-Fi, or maybe it connects to other things as well, using Bluetooth or mesh technology, et cetera. And then maybe you use some kind of hub to connect all of those connected things to the internet. There are so many boards to choose from that Make Magazine decided to create an entire website dedicated to helping you choose your board. And there are also a lot of programming languages to choose from when you want to choose a board. And so you may be familiar with Arduino or C++, which is a very popular platform. But there's also boards that you can program with Python. And there are also boards that you can program with JavaScript. It is a great time to be a maker. But today, we are going to talk about a particular microcontroller called a particle electron. This is the board that started it all for me. It connects directly via a cellular connection through a SIM card. Side note, I don't actually work for Particle. I just think that this particular family of microcontrollers is a really effective gateway microcontroller, and I think it'll be yours as well. And another side note, it's got a cousin called the Particle Photon, and it connects via Wi-Fi. But you can use both the code that we will be talking today in both devices. This board requires no downloads because it's got a web IDE, one line of code to connect to the internet, and there are no cables required to flash your code. Interested yet? It's going to be that kind of presentation. There's a lot more puppies in your future. Let's get started. This is the journey that we will take today. First, for the first two sections, we will talk about familiar ground, which is coding. First, we'll learn about that one line of code to the internet, to connect to the internet, and then we'll learn about how the code looks like if you want to control components from your board. And then the last two is going to talk about how we can connect everything together physically. All right. First, I'm going to teach you the hello world of electronics, which is just blinking an LED. And then we're going to turn that LED on and off using the internet. This is the general structure of the code. Anybody here familiar with OpenGL or processing or any sort of animations like that? Yes. OK, fantastic. Then this will be kind of familiar to you. Setup runs once in the beginning, and then loop runs 5 ever. So this is the hello world example. There is already an onboard LED on the board itself, and we set this onboard light value variable to point to where that LED is, D7. And then in setup, first we make sure to set D7 or the onboard light to output mode. That just means we're going to output some voltage into this pin. And then to begin with, we're going to make sure that the LED is off in the beginning. And then it'll enter loop, and it's pretty simple. We write digital write high to turn the LED on. We wait 1 second, and then digital write low to turn the LED off. And then we wait 1 more second, et cetera, ad infinitum. And that's it. That's the hello world of electronics. Now, what if we wanted to turn this LED on and off using the internet? Well, we only have to change this function just slightly. First, we move all of the turning on and off logic into this function called light switch, which accepts a string command. When that command is on, we will turn the LED on, and when the command is off, we will turn the LED off. And this is where the magic comes in. Particle.function. This is your one line of code to connect to the internet. It accepts 2 things. It accepts a string and a function, which we just wrote. And that function needs to accept a string argument. And the magic of this function, of this line of code, is that it allows you to make an HTTP request to a device-specific URL that ends with /light. So this is what that curl command looks like. Anybody here not familiar with curl? OK, most people are familiar with curl. That's awesome. If you're not, that's fine. You can use Postman to achieve the same thing as well. And in a moment, you'll see an easier way. So you basically make an HTTP request to /light following your device URL. And then you send a string command or a string argument with your HTTP request. And that string command gets passed into whatever function that you specified inside particle function, which is our light switch function. And if you didn't want to make this curl request yourself, there's also console.particle.io that will allow you to send those string commands directly to your device. So this is how it looks like. If I go argument on, the LED turns on, the little LED. And if I go off, then the little LED goes off. Hooray, we just made a thing of the internet. Or have we? Well, I guess technically we did, but we should probably figure out a more exciting way, a more exciting thing to do, rather than blinking just one onboard LED on and off, because this puppy is not impressed. So let's talk about blinking many different LED lights from many different colors, and also take a look at the code for triggering movement. This is the first component that I'm going to tell you about. They're called Neopixels, and they are from this company called Adafruit. And it's actually what is inside that shark hat that I just showed you earlier. These are individually addressable RGB LEDs. Translation, they're really colorful lights that you can treat like an array. Each pixel has an index from 0 to however many pixels you have, and an RGB color value. So you can basically program it like you were programming an array. We'll take a look at a few examples here, and all of these examples are going to be called in that big loop function that we just saw earlier, with some RGB values. So here's one example of blinking just one pixel on the Neopixel strip. First, we call set pixel color on the 0th index, and then we pass in whatever RGB value, and then we call strip.show to update the entire strip and show the color, and then we delay for 1 second. And then in the next second, we call set pixel color again, but with a 000 as an RGB value, which turns it off, and then we show, and then we delay again for a second. So that's how you get this blinking effect. And then after that, if you want to blink all of the lights, you can just move the set pixel color into a for loop that goes through all of your pixels, and then sets the color and then shows it. And then you do the same thing for turning it off. And my favorite, if you wanted to achieve this sort of rainbow rain effect, you can count backwards from the top of the pixels to the bottom, and then put all of these function calls into the for loop so that you show every time you update a color. Cool. And now that you know how to program Neopixel strips, these actually come in a variety of forms. So now you can program matrices and rings and little jewels, etc. Now let's talk about a different component, just for fun. These are called servos. They're servos, not server. I always get that mixed up. They move, they're motors, and they move to the angle that you specify. So you just give it an angle, and then it moves to that position. And this is an example of how it looks like. This is an audience quality meter, and it looks like you are doing amazing. Congratulations. And it's the same kind of idea. You write a quality meter function that accepts some string, and then you set up particle function, and then you make an HTTP request to /audience, and whatever string command that you pass through there will get passed to your firmware function that you specified. Oh, so after you learn about all of these code components, then the rest of it becomes kind of stuff that you already know. For example, you can make an event receiver server that receives events via webhooks from the Uber API, and then update your project accordingly with the correct string argument to trigger the correct animation. Or you can create an event polling server, and that server might poll the Twitter API to search for a particular hashtag, and then you update your project again. Or you can create a Google Voice command and then set up your own Dialogflow instance, and then also turn on your project. You get the idea. This is stuff that you already know. Like I said earlier, you are already halfway there. Oops. Don't want to let you miss that puppy. We are kind of like this puppy right now. We're almost out of the bowl. We are almost able to control a thing that's not an LED from the internet. But obviously, we are all also very cute. So at this point, we already know what the code looks like for connecting to the internet, connecting your board itself to the internet with that one line of code. And then we also know how to control a couple of very common components, such as lights and triggering movement via servos. But if you're anything like past Charlyn, right now you're wondering, how do I actually connect all of these things together with wires and batteries and stuff? This is stuff that I had to struggle with as well, and stuff that was really intimidating. So we're going to talk about circuit connections, or stuff that I wish someone had told me earlier. And we'll dive a little bit deeper into this section because this might be the knowledge that's a little bit more familiar to those in the room. So here's some extra puppies for encouragement. I hope you're not desensitized yet. All right, let's do it. All right, first you take your board and then you flip it to the side like this. You'll notice that there's a bunch of pins sticking out on the side, and these are basically, you can kind of think of them as ports on your computer. They allow you to connect peripheral devices to the board itself, such as the servo or the Neopixels. They're called pins. And each pin has a specific purpose. It's got a specific purpose, and you will find out what that purpose is in this pinout diagram. Now, don't worry, I know that this pinout diagram is kind of really dense and really scary, but there's actually only a couple of things that you need to know to get started. Number one, there's always going to be a way to power the microcontroller, give power to the board. And number two, there's going to be a way to get data out of the microcontroller and data into the microcontroller. So you would get data out of it if you wanted to display something like trigger movement or lights, and you would get data into it if you were trying to sense anything from the environment. Let me give you some tips on how to sort of navigate your way around this. You'll notice that there are pins that contain, that start with the letter D. That typically means that it is a data pin. And each data pin has like different capabilities as well, and that'll depend on the component that you're connecting to it. But this is a good place to start. And then there will also be a way to power your microcontroller. And usually you will have, in a lot of development boards, a micro USB is what you would use to power it. But there's also this thing called a JST connector. And that stands for Japan Solderless Terminal, but you don't really need to know that. The thing that you need to know is that it's a typical connector, usually for batteries, to connect wires together. And then, if you wanted to go a little bit more pro, you can usually find a VIN, VIN, which stands for voltage in, I believe, and then GND, which is ground, which you need to get power to flow through your entire circuit. But if you're just started, you should probably use the JST or the USB port to power your controller, your microcontroller. Okay, now that we know about the circuit points on the board itself, it's time to talk about what circuit points live on the device that you want to connect to your microcontroller. And it's kind of the same thing. There's always going to be a way to power the component itself, and there's always going to be a way to get data into or out of the device. Not always, but most of the time, you will have a way to get data into it. OK. So this is an example. These are the Neopixel sticks that are inside the Schorknerhorn hat. And one of them is facing front, and one of them is facing the back, so that we can see the pads behind it. And then if we zoom, enhance, and rotate, we can see that there is a ground connection. There is a power connection denoted by 5V DC, which means that this component needs 5 volts to operate. And then there's also a data in pad connection. And so you can kind of see where we're going with this. You can kind of see how these pieces will fit together. All right. Hopefully I have some cat lovers in the audience. Looks like I do have one. This is your reward for sticking with me this far. We're almost there. So the next part that we're going to talk about is testing and building your circuit, also known as the fun part. Oh, I had a joke here. We need a tool. We need one more tool, and it's called a breadboard. Not this bread. Ugh. This is a breadboard. OK, I still gave it. This breadboard is a tool to connect different components of your circuit together temporarily, so that you can test that your circuit is working fine, that electricity is flowing through it, and that your hardware, as well as your code, is doing what you expect. Does that sound familiar? Doesn't that sound like a staging environment? So this is basically your hardware staging environment. And you will typically look at a circuit diagram or make a circuit diagram to sort of communicate where these connections, how these connections should work. And you'll probably want to take a look at this closer a little after. So this is how it's going to work. First, you take your breadboard, and then you connect your board, your microcontroller, to it. And then you take the thing that you want to connect to your breadboard. And notice that I've soldered some wires onto this so we can actually use it with a breadboard. First, you connect ground. It's always important to connect ground first. Ask me how I know. And then when you connect ground, we're going to use this ground rail at the bottom. All of these holes are connected, electrically connected to each other, and everything that needs ground will be connected to this ground rail. And then we will connect the power wire of the Neopixel to the power rail. And same thing, we will connect everything that needs power to this rail, because this entire row is connected to each other. And then we take the data in of the Neopixel, and we stick it into one of the data pins of the microcontroller. And this is how we can control the pixel itself from the microcontroller. And then we connect the board itself to ground. We connect it to power as well. And then we take our battery, and we first take ground first, connect it there, and then connect the power wire onto the circuit. And as soon as you connect that power wire, that entire thing lights up. You see that the microcontroller itself is lit up. And we are ready to test our circuit and our code itself. So at this point, you can actually make that curl request, or if you've already integrated that HTTP request to your app, you can kind of run through it at this point. And this is what the animation looks like. If anyone knows how to make high-res GIFs, please see me after this talk. All right. Now that we know how to connect it in the breadboard, we probably need to, you'd probably want to transfer it to a thing that'll allow you to sort of carry it around and make these circuit connections more permanent. And that's where this proto board comes in. It's kind of like your production environment, I guess. You'd be able to make your circuit connections, solder together your circuit connections so that you can carry around and show people. In this photo, I'm using headers. Once upon a time, I forgot that headers existed, and then I just destroyed my microcontroller. So don't forget, headers exist, and this kind of functions like a breadboard. So it's got holes in it, and all of the pins align to those holes. And then after that, you just transfer all of the circuits that you did from the breadboard to this proto board. And then you can test again, because you want to keep that feedback loop of testing your code and your hardware pretty tight so that you can catch any errors along the way. And then after that, you just make a shark hat, or buy a shark hat in this case, 3D print a unicorn horn, and then build them all together. And that's it. Folks, you have just learned how to create a thing of the internet. I will let you enjoy your newfound knowledge for a little bit while I drink this water, and you can enjoy these puppies. Thank you. So like I mentioned earlier, this project really allowed me to learn a bunch of things about making hardware and making hardware projects, and I've kind of been addicted to making things since then. For example, for my birthday, I made this birthday mailbox printer, and it printed out tweets and Facebook messages for my birthday. I also live streamed it, and my friends really got a kick out of seeing their digital notes turn into physical ones. And then a couple of weeks ago, I lost my clicker before this presentation, and so I made my own. I 3D printed the case, I put my name on it, and this microcontroller is built with JavaScript, or it's programmed with JavaScript. So it's a really cute little controller. And my latest project involves this. Anyone familiar with Bongo Cat? Yes, I got some Bongo Cat people. OK. So this is a meme that's been pretty popular on Twitter, or maybe it's not anymore, I don't know. And I turned it into this robot plush. So first, it reacted to sound, and then I made it react to any Twitter post that contains hashtag Bongo Cat. And I have it right here. And unfortunately, the internet won't connect. But here it is if you wanted to see it later. I enjoy making these projects so much that I was able to hold a workshop where I was able to teach my fellow software engineers how they also could program circuits and make their own wearable devices and solder wires together. It was really fun. Here is a preview of the kits that I made for this workshop. And as you can see, I had way too much fun packaging them together. And this is the wonderful hat zoo that came out of that workshop. It was super satisfying to see the smiles on my friends' faces and to know that they, too, have been inspired to make their own projects. And so to close up, I will leave you with this. As software engineers, we are problem solvers. In fact, we are professional problem solvers. This is what we do. And if we all expanded our collective tool sets, I think we would unlock some great solutions. And let's not forget, we're all creative builders. As programmers, we have control of most things inside of our screen. But there's so much possibility and so much opportunity here to bring your code from behind your screen to beyond it, and so much opportunity to bring delight and joy to people through your code. I hope that our time today has convinced you to go out there and make some people smile and make some code you can hold. Thanks.